Okay, good morning, everyone. So let's start. So in the last lecture, we have went through the course syllabus, um, talking about the structure of our course, our tentative topics, grading policy, homework assignments, course projects, types of projects, right? And milestone for the project, and standard to get different letter grades, and lead policy, ChatGPT policy, and so on, right? Hopefully, this can give you a detailed and a comprehensive information about this class. And again, all the course information are listed, is listed in syllabus and in course website. So you probably want to constantly check the course website to look at, say, the lecture, sharing of the lecture slides, some kind of announcement in the lecture page, and also detailed information about project, right? So we have opened the Kaggle competition in class. That is in-class Kaggle competition. We mentioned that we have two types of class projects. One is called the competitive project. The other is called the exploratory, right? Competitive project means that you're gonna join some in-class Kaggle competition, but it's just open for our class. So do not spread the link, right? So you can take a look at the competition task, the data requirement, and also the protocol to submit your own solution. And then the system will evaluate the performance of your machine learning model and give a rank, okay? So you have 1 to 2 weeks to look at and then make a decision. So later, probably early next week, we're gonna release a homework assignment, which is called like project selection, right? And our TA will ask you to upload your course, your project selection. And if you're doing Kaggle project, they're gonna ask you to provide your username in Kaggle so that can link it to your Umail account. So that's for the grading, right? If you're doing exploratory project, of course, you don't need to register on Kaggle. You just let us know you want to do the exploratory project, and then you need to let us know whether you have a team member now. Okay, so that's mainly about the course information. So now let us go back to the slides. Okay, again, we here emphasize two links. One is pointing to my homepage. The other is pointing to the course website. Please leverage the information in those websites as convenient as you feel convenient as possible, right? So again, we want to emphasize that this course focuses on underlying concepts and algorithm ideas in machine learning. In other words, this is not some kind of like professional training like us teaching you how to leverage existent machine learning libraries like PyTorch or a variety of deep learning libraries. This is not our job, right? But I hope our expectation that after taking this class, it will be very easy for you guys to dive into any cutting edge machine learning software or machine learning research and convert it into your own version. How will you learn? We highly suggest you to take classes in person. This is always an issue in our class, partly might because we always try to record lecture videos and release on the website and for convenience, right? But again, to be efficient in your learning, it is all better to come to the classroom and join the class and interact with the instructor, right? You don't need to replaying the video again and again, right? That is time wasting, right? And finish the homework assignments to deepen understanding. implement your learning models and algorithm by yourself, of course, is like our requirement of the homework assignments, and then doing course project to widen your practical experience about machine learning. On Canvas, feel free to post the questions and feel free to discuss and ask clarification question about homework assignments. Our TAs will watch the Canvas and try to respond to you as early as possible. However, like if you put a question at late night or during the weekends, please be patient. They have their own stuff to do, right? They're also very busy. They probably take another 3 classes or they have to write papers. They usually cannot respond immediately when you post questions on late night or during the weekends or holidays. Any questions so far? Okay. So workload, emphasize again, 6 homework assignments, including homework 0, which is gonna be due this Friday. Right? So if you haven't started, please start right now. And project and a course project and 1 light final exam, which will be online. And it's not difficult. It's just enforce everyone to go over the slides we have discussed throughout the semester. Right? And some warning message, this course is pretty heavy according to the previous feedback. It's mainly in workload, meaning doing the homework assignments and doing course project. Some of the past students complain it can take up to 20 hours per week, but I think it is the extreme, at the most extreme point, right? According to my discussion with students who took this class before, it's typically take like no more than 10 hours every week, right? If you're doing well, if you take class constantly, you digest things correctly, you don't feel any uncomfortable stuff like about the course topic, it shouldn't take like more than 5 hours per week on average, I mean. So I don't want to scare everyone. I just want to give you some kind of cases in case like some students like feel, okay, this is too heavy, this is too much. I don't want to feel like my whole time and energy being occupied this class. Then you can make a choice more wisely, or you might this might be like different from what you're expect, right? This is not easy class. I have to say that this is not easy class, but if you're doing well, if you have like good foundations, you have you'll satisfy all the prerequisites, whether or not you have really taken those classes, but you're good at all the in the background, right? That you're doing well, you're taking class seriously. That won't be very heavy, but that won't be like, okay, you just take class and then spend 1 hour to finish the homework every time. That's not possible. That's not the style of this class. So again, we provide this information, we provide this extreme points. Of course, the vast majority of the students who take the class won't take 20 hours per week, right? But we want to provide some extreme points to give you a sense like it might be very challenging for several or few students, but for most of students, their feedback is that, okay, this course is pretty heavy, but it worth my efforts. If that is your expectation, I think that's a good match. Okay. Any questions so far regarding the course topic and policy, workload, and etc.? Great. Okay. So now we're gonna start with some concrete things, right? We're gonna first give a brief review about basic knowledge, but again, this is not comprehensive, like due to the tight schedule of our topics, we won't be able to go through every important concept in math and statistics and calculus algebra. This is a kind of like a lead to give you a sense like what kind of basic concepts we expect everybody to be familiar with. If you feel uncomfortable or if you feel blurred about definition of those concepts, we highly recommend you to find your old textbooks. We look at, or you can search on Google, or even you can ask ChatGPT to get clarification of those concepts, because we're gonna constantly leverage or utilize those definitions to introduce the algorithm and model design ideas. Okay. So first, we would like to introduce the definition of random events and probabilities, right? So we know that the world is filled with uncertainty, right? So except a few like rare cases, right, or occasion scenarios, like most of the cases, people are not 100% sure about whether something is going to happen or not, right? So people would like a mathematical framework which can characterize, can inference under uncertainty, right? So that's where this probability theory and the statistical learning, not statistical, but just traditional statistics framework are about, right? So the one of the fundamental concept is called random events. So basically you can view like, okay, for some event you're not for sure, you can define as a random events, meaning that it can take some kind of chance to happen or take some chance to not happen, right? One commonly used example to illustrate this is called like tossing a coin, right? You toss a coin, you actually have no idea whether you have heads up or you have two up, right? So, and then we can view whether you heads up, you see a heads up as a random event, right? For some coin, you might have 0.5 chance. For some coins, it depends on the materials of the coins and also your how you toss, right? So so the chance can vary, right? So that means like the outcome is uncertain, right? So we define those kind of event as a random event, and you can also define a set of random events as a new event. Like for example, I can define an event like toss a coin for 5 times. Then the outcome of the event will be how many heads and how many tails, right? And then we can see, okay, I probably see an event A, which has like 3 heads up and 2 tails up, right? And event B is like, okay, the first is tail and second has and third tail, fourth has and fifth tail, right? So of course you have a lot of possible events, right? And the occurrence of each different event might be different as well, right? Then there comes a problem, right? How do we characterize the chance, right? So we introduce this so-called probability, right? So we use probability to measure the chance an event happen. And the probability is a positive number between 0 and 1, right? So when we reference the probability that event A happens, we use this notation, P of A, right? And P of B indicates or represents the probability or the chance that B happens, right? And then given the definition of probability, we can, and also the events, right? We can define some set of like composite events, right? For example, I got event A and I got event B, right? So I can construct a third event. That event tells both A and B happen, right? And using mathematical language, this event can be represented by A intersection with B, right? Does it make sense, right? And I can define a fourth event, which is A or B happens, right? Look at the subtle difference between the two events, right? Both A and B happen. This event is different from A or B happens, right? You see that, right? So A or B happens means that, okay, any of either A or B happen, this should be counted as this event happen, right? But for this one, both A and B happen, that means, okay, this event happens if and only if both A and B happen, right? As literally defined. Right? So in mathematical language, we define A or B happens as the union of A and B, right? And obviously, the probability of A union B will be bigger than the probability of A intersection with B. Does it make sense? Right? So there is a formula on this, right? So we assume that everyone has taken the basic probability class before, so I believe everyone knows that, right? So the probability of A union with B is equal to the probability of A plus probability B subtracted by probability A intersection with B. Does it make sense? Right? And there's a very convenient visualization of those relationships. It's called Venn diagram, right? So gonna oops. This. Okay, so you can draw one circle which represents set A, right? And the area over the circle is viewed as a probability of A happens, right? And you can draw another circle which represents the event B, right? Right? And the probability of A intersection with B, meaning the probability that both A and B happens, is actually the area of this overlapping part, right? And the probability of A union B, meaning A or B happens, right, is the area of the union of these two circles, right? So obviously, the latter is bigger, right? And if you want to calculate the probability of A union B, you can add the area over A, right? Add area over B and subtract the overlapping part, right? Because when you add them together, your overlapping part is counted for twice, right? Okay. If you like to find out the textbook, right, or you can search on the Google. This formula has a general version, right? So basically, suppose you have a set of events, like you have A1, A2, A3 to AN, then the probability of A1 union with A2, union with A3, union with A4 is equal to a lengthy equation, right? Summation of the probability of individual probability subtracted by the joint probability, pairwise joint probability, right? And added triple-wise joint probability, subtracted by, well, I forgot that, but just do combination of all four events together and plus subtract until you enumerate the joint probability of all the events, right? So there's a classical formula on that, and please feel free to search on the web or find it in your probability textbook. Okay. So now we switch to random variables, right? So the even definition is kind of like very natural. It directly associated with our observation, right? Because in practical work, we always view, okay, something happened as some kind of event, and it's very natural to assign probability on that, right? But if you want to do some rigorous analysis, right, you want to do some quantitative analysis, you'd better to associate those random events with some real number, right? Why? Because the mathematics has been developed for 1,000 years. Like people have already built out very rigorous foundations to analyze numbers, like real analysis, right? You can define limit, you can define continuity, you can define derivatives, and all kinds of stuff, right? So if you want to use more advanced analytical techniques to characterize the relationship between those random events, mathematicians try to associate the random events you observe in practice to some kind of numbers in some abstractive number system. That's how the random variables come from. But very roughly speaking, you can view like we want to use some number, like real numbers, like integer numbers, to represent some kind of events. For example, if I toss a coin, right? I know that the event outcomes will either be heads up or tails up, right? Then I can use a number to represent whether you have heads up, right? If you have a heads up, then my random variable take the value 1. Otherwise, the random variable take the value 0, right? And then I can look at the range where your random variable's value falls in, right? For example, if I toss a coin for 5 times, right? And if you look at the outcome, we got 5 random variables, right? X1, X2, X3, X4, and X5. And each random variable indicates, because they are either 1 or 0, they indicate whether that tossing will end up with a heads up, right? And then we can take a look at an event, right? So suppose we want to investigate event. That is, we have less than 3 heads. Then this event can be represented as a simple inequality by the random numbers, right? By the random variables, right? That is x1 plus x2 plus x3 plus x4 plus x5 less than 3, right? This actually represents a particular event, right? And then we can quantify the probability of this event by putting a p over this inequality, right? That's where we have learned from our undergrad school about how we define the random variables and the probability, right? So you can see that actually those inequality gives some kind of range where those random variables will fall in, right? And the range of those random variables fall in indicates some kind of event. And because the original event has some probability, that means this inequality has some probability. Does it make sense? Right? So hopefully it can remind you something, but the rigorous definition of random variables is far more complicated than this. So we just at this level, you can consider like, okay, I'm gonna associate some random events with some number, right? With some number. It could be integer, it could be continuous value, whatever, right? But when we take different value of the random variables, it corresponds to different events. And then that means they have different probabilities. Okay. Okay. And then what are the important properties when we calculate the probability over the events or over the events represented by random variables, right? So here are some like very important, very fundamental facts. So first, the joint probability, can be decomposed as a marginal probability multiplying with the conditional probability. So basically, so by the way, I want to ask, what does P of A B, comma B means? Yes, this is very important. Don't get confused, right? So if you say joint probability, it means intersection. Sorry, it's intersection with B. Don't use union. If you use union, this equality is not correct. Does it make sense? Right? So when we look at the probability of A intersection with B, that is joint probability of B, it is equal to the probability of A times the conditional probability of B happens given A happens. Or the probability that B happens times the conditional probability of A happens given B happens. Does it make sense? And similarly, we can define the probability density of two random variables X and Y, right? So they have the same decomposition structure. The joint probability density of X and Y equals to the marginal density of X times the conditional probability density of P of Y given X, or you can start with Y and the conditional probability of Y given X. Does it make sense? Okay. And when we say two random variables are independent, that means like the happening or the occurrence of one event has nothing to do, has nothing to do with the occurrence of the other random variable, right? So mathematically, independence means the joint probability is the product of the marginal probabilities. So if we can claim that the joint probability of A and B is the same as the product of the marginal probability of A and marginal probability of B, then we claim that A and B are independent to each other. Okay, and similarly, when we talk about random variables, we see two random variables are independent. It means that their joint probability density is equal to the marginal density of X times marginal density of Y. Okay. And from from the structure of the joint probability and the definition of the independence, we can immediately draw a conclusion about independence, right? So that means when we say two random variables are independent to each other, that means their conditional probability density is the same as the marginal density, right? So you see, if you look at two events, right, A and B are independent, that means their joint probability is P of A times P of B, right? And then if you look at the decomposition, right, so if you don't make any assumption, right, if you don't know they're independent, then P of A and B equals to P of B times P of A given B, right? So that basically means P of A given B equals to P of A, right? That means the conditional probability of A happens, conditional B is actually it's just the marginal probability of A happens, right? It gives you another view, like actually the occurrence of A has nothing to do with B, right? Even you condition on that, the chance of A happens doesn't change at all, right? And similar observation, you can see that from the definition of two random variables. It's the same thing, right? And then we can extend the definition of independence to conditional independence. So that means we're going to introduce the third random variable, third random event, right? So we say A and B are independent condition on C if their joint probability condition C is equal to the conditional probability of A, condition C times conditional probability of B, condition C. Does it make sense? Right? That's the definition. So don't ask me why. This is definition. Right? So similarly, the joint density X and Y are conditional independent condition on Z, just means the joint density of X and Y condition on Z is equal to the conditional density of X given Z times conditional density of Y given Z. Okay. So once we have defined the random variables, right? We know random variables is a number, right? It could be a continuous number, it could be an integer number, it could be whatever number you want, right? We can define the expectation and the variance of a random variable, right? So expectation just means, okay, because this random variable is value, it has different chances to take different values, right? And then what is on average that value is, right? That's the definition of expectation. So the expectation is an integral of X times the probability density of X, right? Right, if X is discrete, that integral becomes summation, right? And then you might have like X taking different values, has different probabilities, and those probability take as the weight. And then times X is actually weighted average of X. Does it make sense? Right? And similarly, if I want to take the expectation of a function of X, so remember, a function of random variable is also random variable. And then you just calculate the integral of this function of X and multiply it with the density of X. And then that's it. Any question regarding the definition? Those are all just standard. But the meaning of expectation just means, okay, if X takes this chance to take that value, take a different chance to take this value, and take different chance to take this value, take different chance to this value. On average, what's the value of X will take, right? It is essentially just the weighted average of X takes all possible values and is weighted by the probability density. Does it make sense? Okay, so variance. The definition of variance is yeah, expectation can be 0. It's totally fine. Yeah. Any other question? Okay, great. So the definition of variance is just based upon expectation. So it's a expectation of the square of the random variable subtracted by the square of expectation. So see the difference, right? With the first term, we'll first take the square and take expectation, right? And second one is first take expectation, take square. And it's fairly easy to show that variance is always non-negative. Right? So basically variance indicates how wildly the random variable can be deviated from its mean. Right? So you can imagine that, okay, if it takes a larger chance to take values like far away from the expectation, right, from the mean, it has a larger variance, right? So the larger the variance for random variable, that means the more uncertain about our random variables, right? And there is another common use formula to define variance, which might be intuitive, which is if I believe everyone have seen this formula before. So it is an expectation of X subtracted by its expectation, and then take the square. Does it make sense? Right? You look at the difference between a random variable from its expectation. You take square and then take expectation again. Right? That just means like on average, how far away X is different from its expectation. Right? Yeah. Yeah, see it again. Yeah. Yeah, it doesn't change, right? X expectation of X transpose, of course, is expectation of X transpose, right? Because they're just a set of numbers, right? You form you shape that, it won't change the expectation, right? Yeah. Any other question? It's the same thing. Yeah, you just follow the definition, right? Now you need to replace. Suppose you want to calculate the variance of g of X, right? Now you just replace X by g of X. And that's it. So yeah, for homework 0, there are 1 or 2 questions which ask you to calculate the expectation variance. This is actually just to reinforce the definition, right? So to help reinforce you to like to understand the definition and do the calculation. But this is mainly for like if X is just a number, right? And in many machine learning scenario, X is a vector. It's not just a number. Then that means like when we calculate the variance, we're not just interested in calculate the variance of each individual element in X, right? Suppose you got X, you got a vector, right? You got X1, dot dot dot. You might got X10, right? Suppose this is just a 10-dimensional vector, right? And of course, you can calculate the variance for each individual element in this vector. See X1, variance of X1, variance of X2, and variance of X10, right? But when we apply machine learning or statistical learning, we're often interested in so-called covariance matrix. Covariance matrix is not just a number, it's a matrix. So for a 10-dimensional vector, right, the covariance matrix will be 10 by 10, right? So the definition is as follows, right? It's very similar to the definition for the scalar case, right? But you have to consider the shape, right? So the covariance matrix defined as expectation of x transpose subtracted by expectation of x times expectation of x transpose, right? So you see this will give you a 10 by 10 matrix. Only the diagonal part indicates the variance of each individual element, right? The off diagonal part is actually characterized the correlation or the covariance between two different elements in this vector. Does it make sense? Again, if you feel uncomfortable, just go back and look at the textbook you have used it before, or you can search on the website and to give like a more concrete definition. But here we just want to remind you, there's a definition, it's called covariance matrix. And it actually indicates not only the variance of individual variables inside vector, but also the covariance between different elements in a vector. Okay. And similarly, we can define the so-called conditional expectation and conditional variance. So now I want to ask, what's the definition of conditional expectation? Any thought? Yeah, how do we change this original definition of expectation to calculate conditional expectation? How do you do that? Yeah, that's right. You just replace this probability density of x by probability density of x given y. Yeah, yeah. Sorry, man. I don't know. Maybe there's a better place I can place my. Okay, the mouse doesn't work. But anyway, if we just replace the probability density with the conditional probability density, that is, I replace P of x by P of x given y, then this integral will give you the conditional expectation. Does it make sense? Right? One thing to be very careful, the conditional expectation is also a random variable. Why? Yeah, but y is a function random variable. Yeah, because when you shove this P of x given y into this integral, when you do the integration, it will become a function of y, right? That means your conditional expectation actually depends on y, right? And y is a random variable, then the conditional expectation must be a random variable as well, right? So this is a very, very important, right? Don't get confused. You must see some bonus question in our homework 0 asking you to take an additional expectation over the conditional expectation. Don't feel weird. That's definitely a reasonable request. Okay. And similarly, we can compute the conditional variance, right? So basically, what you're doing is that you're gonna compute the conditional expectation of x squared given y, right? And subtract it by the square of conditional expectation of x given y. You got a conditional variance, right? Does it make sense? Okay. Any questions so far? Great. So Next, we're going to introduce a very important concept called the convex functions, right? So a convex function is a family of very simple functions defined on a particular type of domains called convex region or convex set. So what does the convex set mean, right? It just means, intuitively, it just means the domain must be outward, right? You cannot have some kind of like inward part like this kidney shape, right? So more formally speaking, if you pick up any 2 points in this domain, and you can connect them with a line segment, right? It requires every point on this line segment must be inside the domain. It's called convex set. So if you look at the left region, right, you can pick up arbitrary 2 points x and y, and if you connect them, you look at this black segment, right? You see every point on this black segment is inside this domain. So it is called a convex domain or convex region. If you look at this one, right, the right-hand side, right, this guy, right, I can pick up x and y here, and you see when I connect x and y, there are part of the segment which is outside the domain. That means those red segments are outside domain. They are not included in this domain. Then this domain is not counted as a convex region. This region is non-convex. Does it make sense? So it basically requires that, okay, for a convex domain, any points between 2 points in the sense of like line, right, must belong to the same domain. Okay, and based on this definition, we can define the so-called convex function, right? So a convex function is a particular type of functions where the input domain must be a convex region, right? And then it needs to satisfy this inequality. So basically that means, okay, if we pick up arbitrary 2 points from your domain, of course, these 2 points should be different, right? And then if you do a linear combination between any 2 points, by linear combination, that means I connect x1, x2, I pick up arbitrary point in between. And if you evaluate the function in this middle point between x1 and x2, it should be less than or equal to the combination of the function value at x1 and x2. So this is called convex inequality. So this definition seems a little bit unintuitive, right? But it will be a lot easier to understand if we use a figure, right, to show that, right? So this black line is one instance of a convex function, right? So according to the definition, I can randomly pick up 2 points, x1, x2, right, in its domain, right? So I can randomly pick up a t, which is between 0 and 1, right? And then I do a combination of x1, x2 to get the point in the middle, right? So remember, tx1 plus 1 minus tx2 must give you some point in between, right? So the convex inequality tells us that if you evaluate your function f at this combination of the input, it will be less than or equal to, you first evaluate f at x1, and then evaluate f at x2, and then do a same linear combination with t, which will give you the value at here. So you can see that the combination of the function values according to t is actually bigger than you first do the combination of the input and then do the function evaluation. So this is called convex inequality. Does it make sense? Right, that's the definition. Okay. So you can imagine that almost all the convex function has some kind of shape, right? So like a pen, right? Not a pen, like a pot, right? Like a pot is you have some like curve like below and then up. It's always like this, and that kind of curve will guarantee you this, right? You can arbitrarily pick another 2 points and arbitrarily take points in between you always see that, okay, the function evaluate at the linear combination between the 2 points. It will be less than or equal to first do the function evaluation on the 2 endpoints and do the combination. Okay. So several commonly used the convex functions. Exponential function is convex. Negative logarithm of x is convex. Convex function can be also like multi-dimensional function, like 2-dimensional function, 3-dimensional function. That's also okay. Like a very commonly used multivariate convex function is quadratic function. Okay. Then there's a question, right? Suppose you're given a convex function, right? You can use the definition to check whether this function is convex or not, right? But it's not always very convenient to do this check, right? And there are a variety of other ways of testing this, right? So these are 2 commonly used ones, right? One is that if you have a convex function and it's differentiable, then if for 2 arbitrary 2 inputs and x, y, it always satisfies this inequality, then f is a convex function. Does it make sense? So now I want to ask you guys, what does right-hand side mean? What does the right-hand side of this inequality mean? Yeah, there's a gradient, right? So what does that mean? Yes, yes, yes. Yeah, that's what algebraically what does the right-hand side mean? That you're exactly right. But can you can you use some like a geometric explanation of the right-hand side? Yeah, transpose.
Y right here.
Mhm.
So function if the function of y is the y is in red, multiplied by the transpose y because the gradient change in the transpose of the gradient y, which is actually that x minus that x array minus y array is actually
Yeah, that's the algebra. Yeah.
like not integral, but like we're looking at like kind of a like that's like
Yeah. But this is like your explanation is exactly right. It's a definition, right? It's a mathematically or algebraically the definition, right? But here I would like to go one step further, right? So if you look at the right hand side, which is f of y subtracted by x minus y, right? If you look at this right hand side, okay? So it's very similar to what we have learned before about the tangent. So if you draw a function, right? You suppose it's a position right here. If you want to draw a tangent line at this input position y, what's the representation of this tangent line? Okay. The definition of tangent line. So this is slope, right? This guy is slope, right? This is intercept. This guy is x minus 1 0. Yes. Yeah. If you look at just the normal plane, right? This is just like fx, not fx, just g of x is equal to at y subtracted by prime y and x minus 1. Right? It just tell you, okay, if there's a curve called f, right, called fx, right? And if you want to draw a tangent line at a particular location, this is the line. Right?
And that's graded, so that little representation graded, y array transpose.
Yes.
That little thing is the hyperplane.
Yes.
And we're just looking at the 2D representation. We could expand it to 3D, 4D.
You can expand it to whatever it is.
It's the same thing.
Yeah.
Yeah. We'll just.
All right. Okay, that's great. Okay, everyone is comfortable with this? The geometric meaning, right? So now, if you look at the inequality, right? This just tells us that if you look at the meaning from a geometric perspective, it just means that the whole function body, if f is a convex, right, must stay above any underline, right? That's actually what this inequality reflects. Remember, this must hold for arbitrary x, y in the domain, right? So that means when you vary y, you vary another position, right? You can draw another tangent line, right? And this inequality holds as well. Why? Because the whole function body is always stay above the tangent line. So that's the insight on the line with seemingly boring inequality. Okay. And another common used rule to check whether this function is convex or not is just to take a look at the Hessian of the function. Of course, you have to assume this function is twice differentiable, right? And if this Hessian matrix is positive semi-definite, then we can claim that the function f is convex. And this definition is not that intuitive. I mean, this the proof of this is not very intuitive, but you can still find this as classical proof for this, right? If you're interested, you can search on the web and look at the proof. It's not hard. It just leverage the directional derivatives and then use convex functions definition. Okay, so associated with can you repeat your question? Okay, so if you definition you make it not be less than or equal to, and you invert it, it's bigger than or equal to. This is called concave function. Okay, but convex function is like convex and concave is like a mirror, like a mirror, two sides in the mirror, right? And they have many similar properties, except that it is kind of opposite, right? So when we see a function is convex, and if it has a local minimum, that means it has a global minimum. And when we see a concave, well, concave function is always something like this. We will have a local maximum, it will always be a global maximum. We'll mention this concept again when we talk about the relevant machine learning models. Any other question?
Notation that there is that less than 0. That was representation.
Okay, that's good. So this notation usually means positive semi-definite. Positive semi-definite. It means a matrix, right? If you got a matrix, right, you can calculate the eigenvalue, right? If all the eigenvalue is non-negative, it's called positive semi-definite. Right? Yeah. Yeah, that's a very good question. Any other question regarding the notation? Okay, great. Okay, associated with convex function is this so-called Jensen's inequality, which is very widely used, very fundamental. So what does Jensen's inequality tell us? It just tells us that, okay, if you got random variable x, right, and your f is convex, then this inequality always holds. So that means if you take expectation of x and then evaluate your f at its expectation is less than or equal to, you take expectation over f of x. Remember, x is random variable, f of x is also random variable, right? The expectation of fx is a value, right? It has own definition, right? So Jensen equality tells us, okay, the convex function of expectation of a random variable is less than or equal to expectation of a function of the convex function of a random variable. Right? And similarly, you can replace x by arbitrary function of x. This still holds, right? Because g of x is another random variable. So this serves as kind of like fundamental rule in not fundamental rule, a fundamental tool to do like modern machine learning, right? You see many cutting edge methods like generative models. They're based on the so-called variational inference framework. And the derivation of variational inference framework is based upon Jensen's equality. You see their loss function is actually derived by this. What? Yeah, only f, right? Not g. G is, I mean, okay, I have a random variable x, right? Then g of x is also a random variable, and that's it. So you just leverage this conclusion again. You get the same inequality. Okay. Any other question? Perfect. Okay. So the last thing we want to mention is about the matrix and vector derivatives. So those are not as important as maybe 5 years ago, because modern machine learning libraries, they all implement computational graph and automatic differentiation. So you don't need to manually derive very complex derivatives, right? But when I was a graduate student, we have to manually derive the gradient of your loss function with respect to different matrices and vectors in highly complex functions. So it's not a fun thing, right? And but here we share this basic facts, and also the related reference is just for your reference, right? So if you want to calculate a derivative of a function with respect to some matrices and vectors, what are the common used facts, right? And like a derivative of a constant matrix is simply 0. It's very similar to the number case, right? The derivative of a scalar times a matrix random variable is the scalar times the derivative of the matrix random variable. And you can see there are a bunch of rules here, right? The derivative of the summation is equal to the summation of derivatives, right? And the derivative of the multiplication, you see that it's kind of similar to the number cases which we have learned from calculus 1, right? But there are some other more complicated cases, like if we want to take the partial derivative of a Kronecker product between two random variables, right? And x, y can be both matrices, right? So how do you decompose them, right? And if you want to take the derivative of a determinant of a random matrix, suppose that, yeah, and then it can be decomposed in this form. So again, these are just the facts. You don't need to prove why this is the truth, right? These have already been discovered and rigorously proved by prior mathematicians, right? Those are just the facts. If they're useful, you can leverage them. and you can just apply them. It's just like you apply the chain rule recursively and to get your final results. And here we just add additional set of rules about matrix derivatives, and when you derive everything, you shove them into that and to simplify the results now until you get the final result. Does it make sense? Okay, that's all about our basic knowledge review. Any questions so far? Everyone feels comfortable? Okay, again, this is not a comprehensive review due to the time limit. We won't be able to do a comprehensive review. This is just like a lead to give you like sense, okay, what kind of definitions and calculations we would like you to know before we proceed to some detailed machine learning frameworks, right? For example, expectation, variance, those kind of stuff are very important for us to understand stochastic gradient descent, right? And especially the variance, those kind of stuff, when we talk about the sample complexity bound, you need to have the concept, right? Why we have sample complexity bound? Why the bound is random variable? It's not a deterministic one, right? So you must be you need to be realize that this is because the bound itself is also random variable. Again, if you feel uncomfortable about anything about this, right, please feel free to open the past test post you haven't read before, or you just search on the web and to kind of like strengthen your impression about those concepts, because those are really, really important in our future discussion. Okay, next we're gonna start introducing supervised learning framework. So now we kind of start with so-called machine learning, right? So as we mentioned before, right, our whole class will focus mostly on this so-called supervised learning framework. So basically, you have training data, right? Your training data are a set of labeled instances. We hope that your machine learning models can learn something from those labeled instances. This is called supervised learning. It's like, okay, I give you a pile of mathematical problems and also answers, right? And you want to, by reading those answers for those problems, you want to summarize some kind of patterns or rules to solve problems of the same type, right? And then you can generalize to different problems. Right? So we're going to first introduce the framework of supervised learning, and then we're going to start with our first machine learning algorithm, which is called decision tree. Okay. So first word is supervised learning. Right? When we design supervised learning tasks, right, we should be clear about what are the instances and what are the labels, right? So here we want to introduce a concrete task, right? Suppose we have a task, right? We want to automatically tag news articles, right? But this is actually a very fundamental task in any major news website, right? They want to generate personalized recommendation about news, right? Some users would favor like sports news. Some users are fan of political news. Some users like they only look at the financial news, right? So that means, but every time like news articles, like every minute might generate 200 news articles all over the world, right? You need some like automatic tool to classify those news articles and then look at and then do the recommendation according to the labels, right? So that gives us this task, right? So suppose you're given an arbitrary news article, right? Can we tag it as one particular type, right? One particular label, maybe sports, right? Maybe business, maybe politics, maybe entertainment, maybe financial, and so on, right? So you can imagine that because you have so many possible news articles, right? So we define all possible news articles as the so-called instance space, right? Every particular news article is viewed as one instance, right? And then we can define an instance space which contains all possible news articles generated in this world, right? On the other hand, we also need to look at what are the possible labels we could tag on each news article, right? And that is predefined by us, right? We want to predefine maybe 20 labels, right? Sports, business, politics, entertainment, financial, gossip, and whatever, right? Like, and then our task would be map an arbitrary news article in this instance space to one label in this so-called label space, right? So this comes our framework. Okay? So you see that we have an instance space which contains all possible news articles, right? We have a label space which contains all possible labels we could tag on each news article. Then our task essentially is to find out a mapping, right? Which map one instance in the instance space to one label in the label space. Right? So this is called supervised learning. Right? So now we give a more general yet more abstractive definition. Right? So in general, when we conduct supervised learning, we're going to have an instance space. The instance space is the set of all possible examples that need to be classified. And meanwhile, we need to define a so-called label space. As the name suggests, right? The label space includes the set of all possible labels. Right? And the label space actually is determined by your task. For example, if your task is to do like spam email detection, right? Then your label space is just two labels, right? Spam or not spam, right? If you're doing like binary classification, your label space is just either positive or negative label, right? If you're doing like a multi-class classification, like news tagging, you might have 20 labels, right? And then your label space contains multiple labels, right? So actually the label space is really up to the particular application you want to do. Does it make sense? So once we have defined our instance space and label space, we actually have defined our task. Then the next step is to find out a mapping from the instance space to the label space, right? So assume that, okay, there is an underlying ground truth mapping, which we call target function, right? Such that given any instance in the instance space X, this target function can give a ground truth label, right? So this is like image classification, right? You are presented one image, you're gonna give there is some ground truth function that can classify that image correctly, right? Either it contains tag or not, either it contains dog or not, either it contains human faces or not, right? So there is always a ground truth target function who provides the correct label for every instance in the instance space. Right? Any questions so far? And then our goal is to find out such target function from training data. So we'd like to emphasize that this task actually is not trivial. Even some of these tasks might seem trivial to human beings, right? Like for example, if you present an image to human beings, right, we can like immediately tell whether this image contains a human face or not, right? But it's not a trivial task for a computer program. Because what computer program can say is just a set of 0, 1 pixel values and so on, right? But human beings, you can say, okay, the shapes and the faces and the eyes and hairs and all kinds of stuff, right? So we know there is some kind of ground truth function which performs the mapping and which performs the ground truth labeling, right? But we want our machine learning algorithm to discover this function by a collection of labeled training data. Right? So the labeled of training data usually can be represented in pairs like this. Right? I have instances, I have the label generated by the ground truth target function, right? So I got x1, x1's label, x2, x2's label, x3, x label, until xn, xn's label, right? Then we hope that we're gonna have some learning algorithm. When we provide those labeled training data to the learning algorithm, it's gonna find out a learned function G, which is also can label every instance in this instance space, right? But in the best case, we hope that our learned function G will be exactly the same as the ground truth F. That's our ultimate goal of learning, right? Does it make sense? Right? But here I want to tell, like in practice, you want your learned function G to be exactly the same as the ground truth target function F. That is infeasible. In most cases, that won't be feasible, right? So in more practical expectation is that, okay, I want my learned function G to be approximately close enough to F. Then this fulfills our learning procedure. So now we can see this general procedure of conduct supervised learning, right? So you define instance space, which determine which set of data instances you want to handle, right? You define a label space, which determine what kind of classification task or prediction task you want to do, right? And then you're given a collection of labeled training data. You feed this data to some learning algorithm. As to which learning algorithm, we're going to see quite a few, right, in our class, right? And our learning algorithm will generate a learn function G. We hope that our learn function G will be as close to the ground truth labeling function F as possible. That's the whole supervised learning framework. Any questions so far? Does everyone feel comfortable? And throughout this semester, you will see that all the learning algorithms we'll discuss actually is conducting the same procedure. The only difference is how you're going to design different learning algorithms. You see that different learning algorithm design will choose different space to generate this learn function and different way to identify the learn function. Okay. Yeah. 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 Mm-hmm. Any other question? Okay, so this procedure we call supervised learning procedure or supervised learning protocol, right? So now I want to ask, do you have any, can you think of other learning framework or protocols? What if I only provide you the instances without providing any labels, right? If you can fit such kind of unlabeled training data to our learning algorithm, you still learn some function and mapping, and this is called unsupervised learning, right? If you put part of labeled instances and part of unlabeled instances, this is called semi-supervised learning, right? But in whichever, the most important is the so-called supervised learning, because unsupervised learning, semi-supervised learning, they are kind of like very largely just inherit the methodologies and ideas of supervised learning, and do some proper extension. That's why supervised learning is always the most important framework in the machine learning. Okay. Okay, so one last thing I want to emphasize that after our supervised learning, right, our learner will provide some learn function G, right? And we know that there will be some ground truth labeling function F, right? So it's usually very hard for you to directly compare the two functions because you don't know what is the curve for labeling function, right? You don't know any analytical function for F, right? So it is not realistic to directly compare F and G in terms of their expressions, whatever, right? So in practice, people will always like draw test examples. Like in the domain, right? In the instance space, I just randomly draw, say, 1,000 examples or 10,000 examples. I look at the ground truth labeling generated by your ground truth label function F, and you look at the prediction made by a learn function G. Then you just compare whether they are the same, right? If in most cases they are the same, then we could claim, okay, your G is very close to F, right? That means your learning performance is good. Otherwise, if like only 50% of cases your G and F match, in other cases they do not match, that means your learning performance is really bad, right? That's how we conduct testing in supervised learning, right? And in machine learning practice, it is always better to use as many test examples as you can to evaluate performance, because the more test examples you use to check, the more reliable evaluation you can use to look into your learn function G, right? But here's one very important rule, right? You could never use test examples during training. Why? Why you can't use test examples during training? Yeah, let me just shorten your answer. So basically, you can, if you use test examples during training, you can very easily do cheating, right? You can just memorize test examples, right? And then your test error is always 0. But that doesn't mean your program, your algorithm really learns something useful, right? Okay, so this is very, very important, right? So in your practice, whenever you see, okay, your performance on the test data set is incredibly high, so don't celebrate. First, to check whether you kind of mix your test and training examples. Okay, let's stop here today and see you on Thursday. Hi.
I took